Okay, good morning everyone.
Good morning, sir.
Good morning, sir.
So first of all, let me just talk about the theory of matrices and Leibniz and the derivatives. If you have any problems, as I said on Monday, if you have any difficulties right now, you can ask, or else I'll start with our regular syllabus. Fine. So I guess there is no difficulties. Everyone is good with the syllabus and they're preparing the midterm exam. So fine. So we'll start with our new topic. Is Ilist Theorem. Fine. So first of all, we need to understand what do we mean by a homogeneous function. So what we have studied is homogeneous equation equation of pair of straight lines. This you have studied in your 12th standard. Can anyone tell me what is the equation? So the equation was ax square plus 2xy plus by square. Pair of straight lines passing through origin. I should mention this, passing through origin. So this was the equation. Why do we call it homogeneous? Is because you can observe each and every term over here. The first term, degree is 2. The second term, there are two variables, both of power 1. Total degree of second term is 2. Third term, variable y, degree is 2. So each of the term in this equation is of degree 2. Okay. So whenever we look at an equation in which every term has the same power, such a equation is called the homogeneous equation. So this is a rough definition. Okay. So how do we plot this definition mathematically? So a function f of x, y, z is equal to u is said to be homogeneous of degree n of degree n if f of tx comma ty comma tz is equal to t raised to n f of x y z. So I have written the definition for three variables. The same thing can be written for two variables also, as f of x comma y is equal to t, f of tx comma ty. So f of tx comma ty I can write as t raised to n f of x comma y. Now, so this is again the second definition. So from the first one, I can just simply orally define the, yes, this is a homogeneous function. Then in the second one, I can prove the function f of xy homogeneous by considering f of tx comma ty. And the third definition will be, say you have a function f of x comma y, then I can convert it to the form y by x. Then we'll see some of the examples of this. So if f of x comma y can be written in the form of x raised to n g of y by x, or y raised to n capital F of x by y, then f of x comma y is homogeneous of degree n. This is the third way by which I can identify a homogeneous function and its degree. Okay, so look at some of the examples and I will find the degree by both the ways, and also I will prove that those are homogeneous. So example number one, the same one which we started with, f of x comma y is equal to ax square plus 2hxy plus by square. So consider f of tx comma ty. So this is equal to a into tx whole square plus 2h in bracket tx ty plus b ty whole square. So this is t square, I can take common from the equation, and what we have is ax square plus 2hxy plus by square. So this is t square f of x comma y. So f of xy is homogeneous and it is of degree 2. The other way I spoke about, f of xy is equal to ax square plus 2hxy plus by square. So what I can do is I can take x square common. So what we have, a plus 2h y by x plus b y by x whole square. So what we have got, x square. So I can put y by x as t. So I can say that this is the function of y by x. Fine. Example number 2. F of x comma y is equal to u plus v upon u minus v. Oh, sorry, x plus y upon x minus y. Yes, anyone? Is it homogeneous? If yes, then what degree? Yes, Pratik.
I'm not sure, sir.
Okay, so go with your basic definition then. Yes.
Sir, I think it is homogeneous with degree 1.
Uh, can you please repeat?
Sir, I think it is homogeneous with degree 1.
Degree is 1. No. So let's start with our basic definition.
Sir,
F of Tx comma Ty. So what do you get? Tx plus Ty upon Tx minus Ty. Take T common from numerator as well as denominator. So what we have? X plus y, T x minus y. So T will get cancelled out. So I can write this as T raised to 0 f of x comma y. So yes, this function is homogeneous and it is of degree 0. Now degree 0. Third, f of x comma y is equal to x cubed plus y cubed upon x square minus y square. Anyone?
Sir, homogeneous with degree 1.
Degree
Homo
1.
Homogeneous with degree 1. Exactly. Homogeneous of degree 1. Fourth one, f of x comma y is equal to x cubed log of x plus y under root x square minus y square.
sir, homogeneous with degree 3.
Homogeneous
Yes.
with degree 3. Right. The last one, f of x comma y is equal to sine inverse x plus y upon x minus y.
The
So
indeterminate.
indeterminate.
So we cannot determine the degree of this equation
Why?
because we cannot determine degrees of functions which are in inverse and the other
Look,
complex
you
function.
you start with tx comma ty and see if you could get to what you require, t raised to n f of x y. So sine inverse of
Sir,
tx,
homogeneous with degree 0.
tx minus ty. So t from the numerator and denominator will get cancelled out. So that is outside I can write as t raised to 0 sine inverse of x plus y upon x minus y. So this is what I require, right? F of tx comma ty is equal to t raised to n f of xy. So I can say that yes, it is homogeneous and degree is 0. Am I clear? Homogeneous. What I want on the other side is f of xy once again, and I have to eliminate t completely throughout the equation. Homogeneous of degree 0. Fifth one, f of x comma y is equal to log of x square by y.
Not homogeneous, sir.
So this is not homogeneous. But we can convert this. Okay, how can I convert this if I call this z? Log of x square by y. So log on the other side will become e to the power z is equal to x square by y. Look now, this x square by y, the right hand side, this is homogeneous and it is of degree 1. Okay, I am please note this question down because this will play a greater role than these homogeneous. So this actually the given function is not homogeneous, but it can be converted to homogeneous by sending this log on the other side. Okay, fine. So we have clearly understood what do we mean by homogeneous functions. So we'll write down the Ilist theorem. If u is a homogeneous function of x comma y of degree n, that is u is equal to f of x comma y, then what I can write is x into partial derivative of u with respect to x plus y into partial derivative of u with respect to y is equal to n into u. Also, from this I can also define as from above equation what we can derive is x square second derivative of u with respect to x square plus 2xy second derivative of u with respect to x with respect to y plus y square second derivative of u with respect to y. This is equal to n into n minus 1 times u. So this can be derived, and how it can be derived is you differentiate this with respect to x first, differentiate with respect to x. The same equation I will differentiate with respect to y, with respect to y. Later we are going to add and subtract in order to get the required equation. Okay, so that's why this is also called as the deduction from the given Ilist theorem. But while solving examples, we will be directly using this. Okay, you can try this. How can we derive this second equation from the first one? It will be a good exercise. Fine. So you can also remember this x square second derivative of u with respect to x square plus 2xy second derivative of u with respect to xy plus y square second derivative of u with respect to y square is n into n minus 1 times u. Note that u is directly homogeneous of degree n. So this is the case, then I can directly give the answer for this expression x into partial derivative of u with respect to x plus y partial derivative of u with respect to y also for this equation. So look, this is of I mean, you don't need to find any derivative, any of the thing. You can directly give the answer for those expressions. Those are actually difficult to find. Okay, so that's why Ilist theorem is a very strong theorem. And whenever you see this kind of expression, x into u with respect to x, y, u with respect to y, the first priority should always be given to the Ilist theorem. In the two cases, what we have done is we have written u is equal to function of xy. So there is nothing particular about those two variables. So we will start with the remarks. The first one, if u is the function of x, y, z, u is homogeneous of degree n, then by Euler's theorem, x into partial derivative of u with respect to x plus y into partial derivative of u with respect to y plus z into partial derivative of u with respect to z. This is equal to n into u. Okay. Now, second remark. If z is a homogeneous function of x comma y of degree n, and that is equal to f of u, then x partial derivative of u with respect to x plus y partial derivative of u with respect to y, this is equal to n into f of u upon f dash of u. Again, a very important remark I should say, because we have just now seen that function in our examples. So what was it? The u was written as, so u is equal to sine inverse of x square plus y square upon x minus y. Okay, so this type of function. So this is not homogeneous. You can see that you will get x in the numerator which cannot be took outside. But I can make certain changes in this. How can I change this? I can write this as sine u is equal to x square plus y square upon x minus y. So this part is homogeneous here. And I can call this z. So z is equal to f of u is equal to homogeneous of degree 1. So in this type of cases where your original given thing is not homogeneous, but you can convert it to a function which will become homogeneous. In that cases, we can use this. And in if you are lucky enough to give theory exam, then this deduction will be very important because almost 60 to 70% questions depend on this. Okay, so the result says that your u is equal to f of xy is not homogeneous, but you can say change it to a homogeneous function f of u. F of u will become homogeneous of degree n. Then x into u with respect to x plus y into partial derivative of u with respect to y is equal to n into f of u upon f dash of u. Third one. So I'll call this z is homogeneous of x comma y of degree n and z is equal to f of u. Then x square second derivative of u with respect to x square plus 2xy second derivative of u with respect to x y plus y square second derivative of u with respect to y square is equal to g of u in bracket g dash of u minus 1, where g of u is equal to n into f of u upon f dash of u. Okay, so this is just the next case of your remark number 2 where you had this homogeneous function of degree n. Okay, so in the previous one I was taking the right hand side as n into f of u upon f dash of u. So that was x into u with respect to x plus y into partial derivative of u with respect to y. Okay, so I will call the right hand side in this case as g of u, and for the second derivative term my answer will be g of u into g dash of u minus 1. Fine. So these are all the deductions for the Ilist theorem. So we can go for the examples now. Example: if Hello.
Yes, sir.
Yeah. So sine inverse root x minus root y upon root x plus root y. Then find x u with respect to x plus y u with respect to y. So f of x comma y here is sine inverse of under root x minus under root y upon under root x plus under root y. So f of tx comma ty will be equal to sine inverse of root tx minus root ty upon under root tx plus root ty. So root t will get cancelled out from the numerator and the denominator. So what we get is sine t raised to 0 sine inverse of root x minus root y upon root x plus root y. So u is homogeneous of degree 0. U homogeneous of degree 0. So by Ilist theorem, x into u with respect to x plus y into u with respect to y will be equal to 0 into u. So the answer for the required expression is 0. Fine. Next question. So if u is equal to tan inverse of x cube plus y cube upon x minus y, then prove that x square divided to y divided x square plus 2xy divided to u by divided x divided y plus y square divided to u by divided y square is equal to 1 minus 4 sine square u to sine 2u. Now, so my first question is u homogeneous.
No, sir.
So u is
No, sir.
not homogeneous, but we can make a proper change in this so that it will become homogeneous. So now u is not homogeneous. Tan u is equal to u plus y cube upon x minus y. So I'll call this z. So z is equal to f of u is homogeneous. of degree
2.
so by Ilist theorem what do we have? X partial derivative of u with respect to x plus y into partial derivative of u with respect to y is equal to which result? Original function is not homogeneous, but you have converted it to homogeneous. You have to use the deduction
n into f of u by f dash u.
so n into f of u upon f dash of u. What is our f of u in this case? Tan u. So this will be 2 times tan u upon sec square u, which can be simplified. You get x into ux plus y into uy is equal to sine upon cos square, so sine 2u. Okay, but we are not supposed to find this. What we need is this expression. So
Sir, only sine to u.
n into f of u upon f dash of u. Sorry, sine 2u. Now x square second derivative of u with respect to x square plus 2xy second derivative of u with respect to x with respect to y plus y square second derivative of u with respect to y square. What was this given by? This was given by g of u into g dash of u minus 1. What is our g of u? Where g of u is equal to n into f of u upon f dash of u. In this example, n into f of u upon f dash of u is nothing but sine 2u. Put the values. Sine 2u, derivative of sine 2u is 2 times cos 2u minus 1. So cos 2u minus 1. 2 cos 2u minus 1. So in order to get the required expression, so we need to do the simplification here. So 2 cos 2u is nothing but 1 minus 2 sine square u minus 1. So this will be equal to sine 2u in bracket 2 minus 1, which is 1 minus 4 sine square u. This is the required thing. And take 2 minutes, try to understand this. If you have any difficulties, you can ask, or else I'll go to the next example. So it means that it is clear to everyone. So I will give you immediately one example to solve. Example, if u is equal to sine inverse x plus y upon root x plus root y. Then prove that x square second derivative of u with respect to x plus 2xy second derivative of u with respect to x with respect to y plus y square second derivative of u with respect to y square is equal to 1 by 4 tan cube u minus tan u. Do it. You have 2 minutes. If you don't understand anything, ask. So first of all, tell me the degree. Is it homogeneous?
Sine u will be homogeneous,
No,
not
sir.
u.
So sin u is equal to x plus y upon root x plus root y. Sin u is homogeneous of degree
1 by 2.
1 by 2.
1 by 2. So x into ux plus y into uy will be equal to so it is equal to
2 tan u.
yes tan u. So
Sir, 2 tan u.
2 times tan u. And now your g
Sir,
of u,
half tan u, no?
no, yes, 1 by 2 tan u. So g of u is equal to 1 by 2 tan u. So our x square uxx plus 2xy uxy plus y square uyy will be equal to, what is the formula?
So g of u into g dash of u minus 1.
G of u into g dash of u minus 1. So this is 1 by 2 tan u in bracket sec square u minus 1. Sec square u can be written as 1 plus tan square is equal to sec square. So 1 by 2 tan u in bracket 1 plus tan square u minus 1, right?
Sir, sec square u upon 2.
1 by 2. Yes. So this will be 1 by 2 tan square u by 2. So this can be further simplified, and that will be 1 by 2 tan u in bracket 1 by 2 minus 1. So it will be tan square u by 2 minus 1 by 2. So that will be 1 by 4 tan cube u minus tan u. Okay. Third, this will be the fourth example. So if u is equal to x cube plus y cube upon y root x plus 1 upon x raised to 7 sine inverse x square plus y square upon x square plus 2xy. Find the value of x square, second derivative of u with respect to x square, plus 2xy, second derivative of u with respect to x with respect to y, plus y square, second derivative of u with respect to y square, plus x into u with respect to x plus y into u with respect to y at 1 comma 2. So is u homogeneous? First question. So both the terms must have same degree if I want u to be homogeneous. In the first one, if you see
No, sir, it is
that
not homogeneous.
in the first, if you see, then the first term is of degree 1 by 2, sorry 3 by 2. Right? And if the second one, if you see, that is of degree -7, right? So what I'm going to do, let v is equal to x cube plus y cube upon y root x, and w is equal to 1 upon x raised to 7 sine inverse x square plus y square upon x square plus 2xy. Now, since u is equal to v plus w, we know that u with respect to x, when I am calculating, that will be v with respect to x plus w with respect to x, right? So all the things will be satisfied since u is equal to v plus w, even for the second derivative, first derivative, and so on. So what I want to do is I will find those expressions for v and w independently and I will add them. Okay. So v is homogeneous of degree, homogeneous of degree. So 3 minus, you will get t cube common from the numerator. 3 minus 1 plus 1 by 2, that is 3 by 2. So 6 minus 3, which is 3, and so the degree will be 3 by 2. And w is homogeneous of degree -7. So x into vx plus y into vy by Ilist theorem will be n into v. N is nothing but 3 by 2. So the answer will be 3 by 2 into v. On the same line, x square vxx plus 2xy vxy plus y square vyy will be equal to, anyone?
N into n minus 1 into v.
So 3 by 2 minus 1 will be 1 by 2 into v. So it is 3 by 4 v. And for W, the same calculations, x into wx plus y into wy is equal to minus 7 into w, and x square wxx plus 2xy wxy plus y square wyy is equal to minus 7 into minus 7 minus 1, which is minus 8 w, right? So this is going to be 56 w. So I'll call this 1, this as 2, this as 3, and this equation as 4. Adding 1, 2, 3, and 4. Okay. While adding, you have to keep in mind that we need u with respect to x, not v and w. So accordingly, we will also have to make the adjustments there. So we'll have x square vxx. So I'll write it down in this manner now. X partial derivative of v with respect to x plus y partial derivative of v with respect to y plus x square partial derivative of v with respect to x square plus 2xy second derivative of v with respect to x and y plus y square second derivative of v with respect to y plus the next terms x partial derivative of w with respect to x, y partial derivative of w with respect to y plus x square second derivative of w with respect to x square plus 2xy second derivative of w with respect to x and y plus y square second derivative of w with respect to y square is equal to, so I'll write down the required term, 3 by 2 into v plus 3 by 4 into v minus 7 into w plus 56 into w. So I can adjust the terms now. So I will have x partial derivative with respect to x v plus w plus y partial derivative with respect to y v plus w. So these terms are going to be u. In the similar manner, x square second derivative with respect to x of v plus w. In the similar manner, I can collect all the terms and I will get the required expression. So this is plus 2xy second derivative with respect to xy in bracket v plus w. And the last term is y square second derivative with respect to y of v plus w. And the final answer is going to be 3 by 2 plus 3 by 4, 9 by 4 v minus 7 plus 56 means 49 w. Fine. Now we have to find this value at the point 1 comma 2. So value of v at 1 comma 2 is something, value of w at 1 comma 2 is something. So I'll just simplify this. X ux plus y uy plus x square uxx plus 2xy uxy plus y square uyy is equal to, the value of v at 1 comma 2 is, v at 1 comma 2 is 9 by 2 and w at 1 comma 2 is 5 by 2. So 9 by 4 into 9 by 2 plus 49 in bracket 5 by 2. So the answer is 81 by 8 plus 49 pi by 2. So that's all about partial differentiation. In the next lecture, we'll start with our last unit, that is Jacobian. If you have any difficulties, you can ask. Put your name and roll number in the chat box.
Excuse me, sir.
Yes.
Actually, I had a difficulty in the last tutorial.
Yes. What was the question?
Sir, let me just check once.
Yes. Should I stop the sharing?
Yes, sir, sure. Sir, in question 2, that is in the objective section, the third question.
The question is sir, in bracket dabba by dabba x plus dabba by dabba y plus dabba by dabba z का whole square into e की power x plus y plus z.
So when there is a square, say for an example, I have this dabba by dabba x plus dabba by dabba y whole square x plus y. So if I'm not wrong, the question is how to apply this operator, right?
Yes, sir.
So I'll write this as dabba by dabba y 2 times x plus y. Open the bracket, first one. So x plus y partial derivative with respect to x will become 1 plus partial derivative of x plus y with respect to y will become 1, right? So dabba by dabba x plus dabba by dabba y of 2. Again I will open the bracket. So second derivative of 2 with derivative of 2 with respect to x is 0, with respect to y is 0. Am I right?
Yes, sir.
Or else otherwise what you can do is you can make this square. So
Okay, so it's just second degree partial derivative.
yes.
Okay, sir.
Fine. Thank you. Don't forget to put your name and roll number.
Thank you, sir.